Hey guys, in this video I'm going to solve this problem. To explain quickly, it's just two pipes welded at a 135-degree angle between each other, and then we apply a wrench at the limit of the second pipe, and then we apply a force at the lowest point of that wrench we're using. The force we're applying to the point C is going in the negative x direction, and what we want to obtain is which is the magnitude of the force we will have to apply to the point C, so as we get a moment around the O point in the C direction of a magnitude of 4,000 Newton meters, okay? Now let's get to it. There are two ways to solve this problem. One is the scalar way, and it's in this specific problem it's easier, but what's the problem with the scalar method? Well, it lacks the generality that we may need in other problems, and it is actually kind of prone to error. So yeah, those are basically the problems of this way, but if you're careful, it's actually simpler. Imagine we are seeing this same problem but downward from the z axis. Here we have the z direction, to the right we have the y direction, and downward we have our x direction, okay? So x, y, and c coming out of the board. If you can see the pipes, the first pipe from O to A goes along the C axis. Then we have our pipe from A to our point, what I called B, that is the point of contact between the wrench and the second pipe. And at last we will have from the point B to the point C, which is the point at which the force is being applied to. So the force will be given in this direction. In the problem they told us that the force was in the minus I direction. Also, I like to write this as minus F in the X direction. It's basically the same. I usually use this because it's like simpler to me. And this is F. Here we have a 90-degree angle. If you remember from the theory, we would have that the magnitude of a torque would be given by the magnitude of the arm times the magnitude of the force multiplied by the sine of the angle between them. In this case, this will be 90 degrees, and sine of 90 degrees is actually equal to 1. Note that this is just taking into account the C component of the torque. So we can write it like here, like this. The magnitude of torque in the C direction. So we will have to calculate the magnitude of R, that is this one. First, we calculate this magnitude. Now, I'm gonna rewrite this little part of the diagram. If we write what would the y coordinate axis, it will be this, and if we write the z direction, it will be in this way. Here, we know that between this vertical pipe and this horizontal line in our new space, we'll know that from here to here there's actually a 90-degree angle. So if there's a 90-degree angle from here to here, there must be the remaining angle to add up to 135 degrees, and that angle actually is equal to 45 degrees. If you see from the top of the diagram, we see that the A and B, the distance from A to B would actually just be this component. That will be the adjacent component of this right triangle. So that will be 0.8 times the cosine of 45. Note that the cosine is because, remember trigonometry, it's because this is the adjacent component. And this will be equal to 0.8 times 1 divided by square root of 2. So this first magnitude will be 0.8 divided by square root of 2. Now we do it exactly the same, but we do it for the remaining part of the problem, that is from B to a new point C, that is where the force is being applied. There's a supposition that we have to make in this problem, that is between these two there's a 90-degree angle. From B to C there's 0.2 meters. We can extend this, and we can see that here we have a triangle itself, and the sum of its three angles has to be equal to 180 degrees. So 180 minus 90 minus 45 will give us the answer, and it will actually be a 45-degree angle as well. If we analyze just the small angle. We know the hypotenuse and the angle, so that will give us that this component 0.2 meters times cosine of 45, and if we recall, cosine of 45 is actually just 1 divided by square root of 2. The distance from B to C would actually be just 0.2 divided by square root of 2. The distance R would be equal to, I'm sorry, I'm gonna write it over here. So the distance R would be 0.8 divided by square root of 2 plus the square root of 2. If we add these two up, it will give us that it is 1 divided by the square root of 2. Okay? That's really the exact solution. We can approximate it to approximately 0.71. That will be this distance. Now, if we see the equation, 71 times F would have to be equal to 4,000. And if we divide 4,000 by 0.71, we will have that F would be approximately equal to 5,633.8 newtons. So what is this? This is the force that we would have to apply at C in the minus x direction to have a momentum in the C direction of 4,000 Newton meters. As I mentioned you earlier, there is a way to solve this by vectors. I like this more, even though it's a harder way or maybe a longer way, but I feel this way is less prone to error. This one actually uses the vector definition. Torque or moment for our engineering friends, it's equal to R cross F. It actually uses the vector definition of the problem. Which vector is R? In 3 dimensions, we have to look at the vector. It will be from 0 to C. Now, we can see that OC, the vector from O to C, would be equal to the vector OA plus the vector AB plus the vector BC. We can write the 3 vectors separately, and we'll have that OA would actually be the vector with 0 in x, 0 in y, and 0.6 in the z direction. The vector AB, we have to rewrite that little diagram again. AB, C, easy as one. Now, if we recall, this is the vertical line. It will be set, and this will be 45, and this will be 45. I calculated it earlier in the video, so I'm just writing it down. And this will be equal to 0.2 meters, and this will be equal to 0.8 meters. So now AB will be from here to here. We decompose it in these components, and it's know that this direction is actually the positive direction of y. So this component would actually be 0.8 times cosine of the angle 45. So it's 0.8 divided by the square root of 2. This component would actually be 0.8, but now is the opposing cathetus, and we know that this will be, instead of a cosine, we put a sine, but remember that a sine of 45 is actually equal to the cosine of 45, so we will have 0.8 to 1 divided by the square root of 2. We'll have 0 in the x direction, and 0.8 divided by the square root of 2, comma, in the y direction, and 0.8 divided by square root of 2 in the z direction. Now we do exactly the same for the BC vector, and we have 0 in the x component. We have a 0 x component of BC. We also know that the adjacent will be 0.2 times cosine of 45 degrees, and the cosine of 45 will actually be just 1 divided by the square root of 2, and we will have that in the positive y direction, so 0.2 divided by the square root of 2. Now we do the same for the vertical. Now it will be the opposing cathetus, so that will be 0.2 times sine of 45, and remember, sine of 45 is just 1 divided by the square root of 2, so 0.2 divided by square root of 2, and this will be the vector BC. To get the vector OC, remember that R is actually equal to OC. We just add the x component of the 3, so 0 plus 0 plus 0 will be 0 in the x component, would be 0.8 divided by square root of 2, 0.2 divided by square root of 2, and this will be just be equal to 1 divided by the square root of 2. And in the z direction, we will have the same, plus 0.6. We can write this in the approximate form, and this will give us 0.71 Well, this is not equal, this is approximate. 0.71 and 1.31. And this will be our R vector. Now, I'm gonna rewrite it here. And we know that F is given by minus the magnitude of F in X. So it would be given by minus F, 0 and 0 in the Y and Z component. We calculate R cross F. How do we do this? Well, it's more or less simple. We do it by the matrix method. We write X, Y, Z. Then we write the next row with the first vector. That'll be R, 0.71 and 1.31. And now in the third row, we write the second vector. Minus 0 and 0. This is the torque, but note that this is a vector. 0 X component minus 131 multiplied by F in the Y direction, 0.71 times F in the Z direction. Now, going back to the problem, we had that the C component of the torque or the moment had to be equal to 4,000 Newton meters. We equal 0.71 times the magnitude of F to 4,000. We solve for F and we would have 4,000 divided by 0.71, and I don't recall how much it was, but it's the same answer we had before, 5,633.8 newtons. There's a few important things with this method that we have to note. First, here we can see that there is actually a Y direction of the torque. The torque that is trying to rotate this arrangement in this direction, and we know that this is more information that in the other problem we were leaving behind, and there's actually some problems in which we will need the three components of the torque, so it's important to know it. If you found this video helpful, I would really appreciate if you hit the like button, subscribe, and maybe consider giving me a comment down below with any recommendations you may have that may improve the videos, as well as any problems that you wish I could solve. Thank you very much. Or any questions, yeah. Thank you very much. Bye.